All right, welcome back. We've got a bit of a beefy problem ahead of us here. We've got how a full house is drawn, right? You can draw it in any order, but if you end up drawing 5 cards, you have a three of a kind and a pair, that makes a full house. So, how many different ways can we draw 3 kings and 2 queens? Strictly speaking, order doesn't matter, right? I can draw in any order, and if I end up with these things, these 5 things in whatever order, I've got a full house. So hopefully we're thinking about combinations here, because order doesn't matter. But what combinations are we shooting for? Well, what I would recommend is think of it in 3 pieces. First, think of the number of ways to get 3 kings, and then the number of ways to get 2 queens, and then the number of ways we can draw these cards. So I've got, 4 kings in the deck: the king of hearts, the king of diamonds, of spades, and of clubs. So I want 3 of those 4. And order doesn't matter, right? So I'm looking at 4, choose 3. Next up, for getting 2 of my 4 queens, I've got 4, choose 2. And this final factor is actually going to be redundant, unnecessary even, because order doesn't matter. But I've got it in here because there might be some situations in counting theory or probability theory where you might need that third factor. But at any rate, 4, choose 3, we can run the numbers. There are 4 ways to choose exactly 3 things, assuming order doesn't matter. And we can run the numbers there. 4, choose 2 comes out to be 6. And 5, choose 5, right? I'm picking everything. And there's only one way to pick everything, and that is to pick everything. So I'm looking at 4, 6, and 1. Multiplied together gives me 24. There are 24 different ways of getting a full house in a 5-card draw. That is, of course, if you assume order does not matter, which, of course, for 5-card draw, it doesn't. If it did matter, this number would be much, much higher. But it doesn't, so it's not. And this one, honestly, for those of you working with me on WebAssign, is probably one of the harder questions you could be asked, because there are a lot of moving parts that you have to account for. But with a little bit of practice, I think you can pull it off. So just a quick thought here, and this is going to round out this video series. If you're wondering how to find all of these numbers, right? The 5, choose 7. I'm sorry, that's impossible. The 7, choose 5, or the 10, choose 10, or the 4, choose 0, or the 5, choose 3. I don't know. What you can use is the Pascal's triangle. It's pretty neat. It gives you all of those calculations for combinations right from the get-go. So let's see here. We found 4, choose 2 and 4, choose 3. So let me look here at the 4 row. Right, you'll note the top row is the 0 row, 0, choose 0. But we're looking at the 4 row because we are choosing out of 4. And if we choose 0, that's 4, choose 0. 4, choose 1. 4, choose 2 is 6. Hey, that's what we found. 4, choose 4 is 4. Hey, that's what we found. And of course, in the next row, 5, choose 5 is 1. Hey, that's what we found. All of these numbers will give you in choose R where the row is in and the spot, the column, I guess, the diagonal, I should say, is R. And what's just a fun factoid here is to get to the next row down, you take the previous row, slap some 1s on the outside, and add the previous 2 diagonals together. So 6 and 4 make 10, and 10 is now 5, choose 2, and 5, choose 3. And then 10 and 10 come together, and that makes 20, and that is 6, choose 3. And you can go down until you explode from the numbers being too big. That's just a fun thing there. Pascal's triangle is pretty useful in probability theory, and so I'm just throwing it out here. Maybe it'll help you do these combinations quickly. And just a last thing, if you add all these numbers together, for instance, for the 9 row, you add all these numbers together, you get 2 to the 9th power. Pretty nice. All right, that's it.